Section 6.1 Inner Product Length and Orthogonality. So let vector u has coordinates u1 up to u2, vector v has coordinates v1 up to vn. Then if this is a column vector, then u transpose would be a row vector. So then we would change columns to the rows. Then by definition, the inner product or dot product of two vectors u and v is defined as dot product, like with the fat dot or bolded dot, is u transpose times vector v. U transpose is the row vector times the column vector. And when we multiply, it's the same rule as for matrices. So row times column, we would multiply u1 times v1 plus, and we would multiply u2 times v2 plus, and so on. So the dot product does nothing else but multiply row times column. Or if you would like to think, if you look at vector u and vector v, what does dot product do is multiply the entry-wise. u1 v1 plus u2 v2 plus u3 v3 and so on up to un vn. So that's the definition of the dot product. Note that if you add all of them together, what you get is a number. So dot product is a number, not a vector. And then we have an example given two vectors. So we have vector u, vector v, find the dot product, and find this dot product uv divided by dot product of uu. So in that case, dot product of uv is going to be nothing else but -1 times 4 plus 2 times 6. And if you multiply and add them together, you get 8. Now, dot product of uv divided by dot product of uu. So dot product of uv is calculated above, so this would be 8. Dot product of uu would be nothing else but u transpose, which would be the vector -1, 2 times the same vector -1 and 2. And in that case, what we have is nothing else but -1 times -1 plus 2 times 2. And that's exactly what I have right here. So that we basically multiply twice the same. -1 times -1 plus 2 times 2. And that gives me 1 plus 4, which is 5. And please note that if you do dot product, let me see if I can change this. If we did dot product of the same vector, so what's happened right here, dot product of the same vector is nothing else, but if I have this vector u, let's say that vector u has coordinates u1, u2, and we would multiply times u1, u2. I would need to say that what I'm doing is dot product of the same vector, right? Then we would multiply, what would we get? u1 times u1 plus u2 times u2. And u1 times u1 is u1 squared plus u2 squared. So dot product of the same vector is nothing else. Dot product of the same vector is nothing else. You just square the first coordinates and square the second coordinates. That's exactly what it is. And then what we have, I think we have that note here, dot product of uu is u1 squared, u2 squared, and so on. Now we have properties of dot product. So if you have vector u, v, and w be vectors with n coordinates, and let C be a scalar, then the dot product UV is the same as VU, because if you multiply coordinates wise, what we are doing 1 times 2 is the same as 4 times -1. 2 times 6, you can change the order for multiplication of numbers. And if you have U plus V and dot product, you can simply distribute this dot product. And if we have a scalar, so that becomes U dot product W, V dot product W. If you have a scalar, that scalar can go in front or it can go inside the V, that doesn't matter. And U dot product U is always a positive number. It comes from the node below, and that's what we discussed before, because U1 square plus U2 square, any number square is always positive number. So if you add them together, you always get a number, non-negative number, positive number or 0. And for U dot product to be 0, if and only if U is 0, because those numbers are always positive, so there is nothing to cancel out. So in order for the dot product to be 0, we need to have that the U is 0. The length or a norm of a vector U is a non-negative scalar. We're gonna denote with the two straight line. We call it norm. It's a general definition of a length. It's defined as what we do is square root of U1 square, U2 square, and so on. So this is called the length or a norm. And if you square it both sides, the square root and square root would cancel out, and we would get this one. Where did we get this? The length? The length should be straightforward. For a 2 by 2 vector, if I put put for a 2 by 2 vector, so if I put 2 by 2 vector on a number line right here, so then what we have, this would be my x coordinates. So this is my first coordinates, we can call it U1. This would be my second coordinate, we would call it U2. So this is the length. This is the length. So from Pythagorean theorem, we would have that U1 square plus U2 square is equal to C square. And C square is nothing else but the length. Taking square root of both sides, we would get the length formula right here. So now if I have the length formula and I square it both sides, if I would square it both sides, that what I'm getting is U1 squared, U2 squared, and U1 squared, U2 squared, if you look at the note, is nothing else but the dot product. So norm squared or length squared is nothing else but dot product. And if you have C times a vector, that number C, absolute value, can go in front by the definition of the length of the norm. A unit vector is a vector whose length is 1. So now we have an example, given a vector U, 4, 3. Is it possible to find a vector in the same direction as U, whose length is 1? So if we plot this vector on a chart, on a coordinate system, so this vector has 4, 3 coordinates, we would go 4, we're gonna start at 0, we would go 4, 3 up, so this is my vector U. And using Pythagorean theorem, I can see that the length is 5. 4 square plus 3 square. 4 square plus 3 square is we would have 4 square plus 3 square, which is 16 plus 9 is 25. So then if I take square root, so the length of that vector is 25. And if the length is 25, how can I make the vector in the same direction of length 1? I would need to divide this whole vector into 5 equal parts, 1, 2, 3, 4, and 5. My parts are not equal. And then if I take one of them, so what I'm doing is taking 1/5 of my length. So we can find the vector that would be the same direction if I scale it, rescale it, my vector u, take 1/5 of length. So if I take 1/5 of the vector 4, 3, it's 4/5. So what I did, I divided the coordinates of the vector by the length. And that would be the case pretty much in a minute. What we did is take 1 divided by the norm or the length times the vector u. That's what we did right here, right? So we can conclude we can always normalize given vector. That is, we can always find a vector with length 1 in the same direction as the given vector. So for the given vector u, the vector u divided by its length is a unit vector in the same direction as u. U divided by vector by its length or norm is called normalize. So you find the vector in the same direction as the given vector, but with the length 1, you divide it by the norm. So here we have example, find a unit vector in the direction of the given vector. So that vector has coordinates 7, 4, 1/2, and 1. I will call it that vector u. So what I'm doing, I'm finding the length of that vector first. So the length is square root of u1 square plus u2 square in coordinates. So 7, 4 square plus 1/2 square plus 1. 7/4 square is 49/16. 1/2 is 1/4 plus 1. Find common denominator. So this would be, we would need to multiply this times 4, and this is like over 1, so times 16 times 16, right? Then we would have 49 plus 4 plus 16 is 20, 69. So if I take square root of each, I'm having square root of 69 over 4. This is the norm or length. But we need to find unit vector, so we need to rescale it, this vector, dividing by the length, right? One of this one, take it. So unit vector is u divided by the length, or 1 over the length times u. So I'm 1 divided by my length, which is this length, times the coordinates, because I would like to have vector in the same direction, except rescale it. So to divide by a number means multiply times its reciprocal, and then this number multiplied times each coordinates, right? We would have 7 over root 69, 2 over root 69, and so on. There is no minus. It was the size of the vector. So this vector is a unit vector. If we want, we can rationalize. That means take square root of 69 out of the denominator. What I would need to do is to multiply times square root of 69 divided by square root of 69. And I would do for each and every one. Square root of 69 times square root of 69 is square root of 69 squared. So that would cancel out. I'm left with 69. And then I have 7 times square root of 69. And I will do the same for each and every one. So whether you rationalize or not, this is also unit vector. Geometrical interpretation of a dot product for vectors with 2 or 3 coordinates in R2 or R3. The dot product is nothing else but the length of u times the length of w times the cos between them. So if I have 2 vectors, vector u and vector w, and the angle between them, the dot product is nothing else but the length of v times length of W times the cost between them. The geometrical interpretation comes from the law of cosines. If you remember law of cosines, a square is equal to v square u square minus 2 times vw times the cost between them. If you do a little bit manipulation and express each length as a dot product, you will end up with this formula. So this is the geometrical interpretation of the dot product. Now the distance between two vectors u and v is the length of the vector u minus v. That is the distance, with the distance is the length norm u minus v, so you would have square root of the coordinates y's. So we have example, find the distance between u and v. So the distance is the norm or length of u minus v. So we have the norm and we subtract u minus v. So 1 minus negative 1, 2 minus 2 minus 0, 0 minus 3. We're getting this vector, and now we need to find the norm or the length. So we have square root of first coordinate square, second coordinate plus second coordinate square, third coordinate square, and then we perform this, and I believe 8 plus 9, 17. Definition: two vectors u and v are orthogonal to each other if their dot product is 0. Orthogonal means perpendicular. Two vectors are perpendicular. This definition can be justified when the dot product is 0, they are perpendicular or orthogonal. This definition can be justified by from the geometrical interpretation. So here we go. Here we have geometrical interpretation. This vector u gonna be perpendicular to vector v. So here is my vector u. Here's my vector v. Oh, vector v. If the angle between them is 90 degrees, right? That's by definition of perpendicularity, or perpendicular to vectors, right? So if this vector is 90 degrees, cos of 90 degrees is 0. That's why the dot product will be whole 0. So two vectors are orthogonal or perpendicular if the dot product is 0. Dot product is 0. Orthogonal means perpendicular. Now we have Pythagorean theorem written in terms of norm. Two vectors are orthogonal. So in a right triangle, this square is equal to this c square is equal to a square plus b square. So this is a Pythagorean theorem for vectors written in the length of the vector, right? We know that if this is vector u, and this is the vector v, we put the vector u at the end of vector v at the end of vector u, then the resulting vector is u plus v. And then the length we would have it. So orthogonal means perpendicular. Vector u is perpendicular to vector v if Pythagorean theorem holds. Orthogonal complements. So if a vector v is orthogonal to every vector in space W in Rn, then v is said to be orthogonal to that space. So to see it, I call this plane to be my space W. If this plane is my space, those two vectors are in that space. So then vector v is perpendicular to that space if it is perpendicular to any vector in that space. So then orthogonal complement of W will be denoted W by the perpendicular sign in the subscript, and the superscript, I'm sorry. And so this vector is, orthogonal complement is denoted this way, and it is the set of all vectors v that are orthogonal to W. So orthogonal complement would be all set of perpendicular vectors. We can have smaller, bigger, taller, as long as they are, I'm sorry, my hand is a little, as long as they are all perpendicular to my space, that's gonna be denoted and call it the orthogonal complement. A vector x is in that orthogonal complement if and only if x is orthogonal to every vector in a set that spans S. So this is the vectors that those vectors, all of those vectors will be in my orthogonal complement because all the vectors are orthogonal to any vector that spans W. And orthogonal complement is a subspace of Rn for Rn vectors. Now we have theorem that orthogonal complement of row space of A is nothing else but the null space. That is row of A orthogonal complement is nothing else but null space. And orthogonal complement of the column space of A is null space of A transpose. That is column orthogonal complement is null space of A transpose. To see that, I think would be nice to consider what is actually null space. We know that the null space is the solution is set of vectors that AX is equal to 0 vector, right? So the set of vector x, when you multiply times A, gives us 0 vector, is called the null space. Now, if I write my matrix A times my vector x, and this should give us the 0 vector, right? That would be my 0 vector right here. So if I take this row, multiply times my vector x, multiply times my vector x. So then this row, if I denote that row A1, what I'm having is row times column, and we would multiply coordinates wise. So in that case, I have nothing else but the dot product of A1 dot product x, and that gives me the 0 vector. So we see that those vectors, we see that by definition, the rows are orthogonal to the x, that form the null space. So that's why the orthogonal complement of rows is nothing else but null A. And similarly, we will consider the part B of that statement. So, yes.